Okay, we're on page 7 of the math induction packet. Remember that at the very beginning you should always define your your proposition or your what do you call it? Your conjecture. Okay, so for example, in this case here, I would say P subscript n is, and then I would say exactly that. Um, Okay, so you should include that as part of your proof statement. A lot of you are not doing that, maybe because you see that I'm not rewriting it, but I'm always like positioning my P subscript n as so that it kind of like takes advantage of the fact that it's already written here. Okay, so I'm going to make it more explicit here, but you should write that because if you don't write that, then how is the person supposed to know what your P subscript n is? And you're like forever referring to it after that, right? Okay. So in the base case, what we're going to say is we're going to say that n is equal to the first value. And in this case, it tells us that the first value is going to be 1, right? Because n is all positive integers. So we'll say if n equals 1, then what can we say? We can say that, let's see, this last term here would be 1 times 1 factorial, which would just be 1. So the first term is 1, the last term is 1. So basically we have the first term of 1, right? 1 times 1 factorial equals 1. And that is equal to the right side. If you want to, you could do what the book does and you could say left-hand side, and then you could say right-hand side. The right-hand side is n plus 1 factorial, which would be 2 factorial minus 1. 2 factorial minus 1 is equal to 2 minus 1, which is equal to 1 also. So we've proved that the left-hand side is equal to the right-hand side for n equals 1. So we can say that P subscript 1 is true. What is P subscript 1? Well, we already defined that P subscript n is that, so we know that P subscript 1 is if we put in n equals 1 into that statement, okay? Let's go to the step case. So for the step case, we are going to assume that P subscript k is true, and we're going to see what we can say if we assume that. So if P subscript k is true, then the left-hand side is going to be 1 times 1 factorial plus 2 times 2 factorial plus dot, dot, dot. And then the last term is going to be k times k factorial. And that is going to be equal to, because we're assuming it's true, k plus 1 factorial minus 1. Okay, so we're going to assume that's true. And then we are going to go one step further, and we're going to say, what about the k plus 1th case, right? What about the k plus 1th case? So now we're going to write that out. 1 plus 1 factorial, or 1 times 1 factorial. That looks like a plus. 1 times 1 factorial. 1 times 1 factorial. Plus 2 times 2 factorial plus dot, 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 all the way to k times k factorial. And now we're going to have one additional term, which is k plus 1 times k plus 1 factorial. And that's going to equal to, let's see, now we're not writing the right-hand side. We're going to see if we can make the left-hand side look similar to the right-hand side. And the way we're going to do that is we're going to try to figure out if we can do this substitution here. We're going to substitute the left side for the right side. And I can already see that we do have the left side here. The left side is right there, right? So what we can do is we can already substitute the yellow part with k plus 1 factorial minus 1, because we assume that's true, plus k plus 1 times k plus 1 factorial, k plus 1 factorial. And we're going to see what we're going to do with that. So now I have a k plus 1 factorial here. I have a k plus 1 factorial here. What if I rearrange them so that they're kind of together, and then I put the minus 1 at the very end? So then I would have k plus 1 factorial plus k plus 1 factorial times k plus 1. See what I did there? I just put the -1 at the end, and I reverse the order of this and this, okay? Now I'm going to factor out k plus 1 factorial from the first two terms, but not from the last term, because the last term doesn't have one. So I have 1 plus, and then from the second one, I would have left over k plus 1, right? So I would factor out a k plus 1 factorial from the first two terms, these two yellow terms, and then I end up with that. And then I have -1 because I didn't do anything with -1. Now I can add up +1 and +1, and that'll be k plus 2, right? So now basically I have k plus 1 factorial times k plus 2 minus 1. Well, k plus 1 factorial times k plus 2, that's k plus 2 factorial, right? Minus 1. And that's kind of what we wanted the whole time, right? Because if P of k statement, the right-hand side is k plus 1 factorial minus 1, the k plus 1 statement should be, the right side should be k plus 2 factorial minus 1, because that's the equivalent of this, right? So we have shown that for the k plus 1 case, it follows the same rule as P subscript k, right? So now let's go down to the thus part, and we'll say, hey, we do know that 1 times 1 factorial plus 2 times 2 factorial plus ... k plus 1 times k plus 1 factorial, okay, equals, and on the right side, we're going to put what we found, which is k plus 2 factorial minus 1. Okay. So, and we know that's true if the thing that we assumed is true is true. If the thing we assumed is true is true. So we're going to put here that 1 times 1 factorial plus 2 times 2 factorial plus ... plus k times k factorial is equal to k plus 1 factorial minus 1. And finally, since P subscript 1 is true and P k plus 1 is true whenever P of k is true, then P of n is true for n is all positive integers. Right. Yes. Moving on to number 7. Let's see. Get a little bit more space here. Okay. So first of all, remember that at the top you're going to write that the proposition or the conjecture is going to be sequence U subscript n is defined by U1 blah 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 blah. Then blah 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 blah. Okay? So let's start out by looking at the base case, which is going to be for n equals 1 is the first n value. So if n equals 1, what this is basically saying is, hey, I got a first term. I can define all the subsequent terms using this, what we call a recursive formula, whereas instead of using just n to figure out what the term value is, it uses the previous term to figure out what the term value is. So if I know that this is true, that the first term is 5, and the recursive formula to find the subsequent terms is this, then I know that I could explicitly find each term using this formula. Okay, so let's see. If we know that U1 is 5, then we could also, and we know this too, but we could also find U1 by using the explicit formula. Is that true? Let's use the explicit formula. 4 times 1 squared plus 1, that's equal to 4 plus 1 is 5. So it's true, right? They're both the same. So we can use either this rule, which is pretty trivial. We didn't even use the recursive rule. We just looked at the first term. And we can compare it to the explicit rule. And for n equals 1, it works. Okay? So P subscript 1 is true, right? Now look at the step case. So in the step case, we're going to say, instead of U subscript n equals 4n squared plus n, we're going to put u subscript k is equal to 4k squared plus k. Okay, and so we know that's true, or we assume that's true. And now let's take the k plus 1th case. Okay, so the k plus 1th case, let's write down that uk plus 1 is equal to, and we're going to take the left side of it, which is this. So uk plus 1 is equal to uk plus 8k plus 5, right? And now let's try to take advantage of what we said was true, what we assumed to be true, which was this. Let's try to plug that in somehow. And we can put it right there, right? So that we have uk plus 1 equals 4k squared plus k plus 8k plus 5. In this particular case, I think that it's good to know where we're trying to go. So like, for example, this is the kth rule, right? For the k plus 1th rule, what we want is we want to end up with this. uk plus 1 equals 4 times k plus 1 squared plus k plus 1. Okay, so this is where we want to go. And let's compare it to what we got here. If we want to make this go to this, then looks like we need to rearrange it so that there's a quadratic here. Just to like see where exactly we're going with this, let's expand it a little bit. We're going to work backwards. And so here we can see we got 4k squared plus 8k plus 4, and here we got k plus 1. And we've separated it in this manner. Are we there? Actually, it looks like we are, aren't we? So if what we're going to do now is we're going to try to divide it up so it's 4k squared, 8k, and 4. So let's do that. We're going to write 4k squared plus 8k plus 4. And then we're going to leave k plus 1 over here. And we do have k plus 1 because the 1 here and the 4 here add up to this 5, right? So if we separate it in this way, now we can factor out the 4 and we're left with k squared plus 2k plus 1. And this is just k plus 1 here. And now it's exactly what we wanted, right? So now we're going to factor k plus 1 squared here plus k plus 1. And this was a little bit tricky, wasn't it? We kind of had to like work a little bit backwards from what we wanted to see how we should rearrange this, okay? And now that we know how to rearrange it, we can see that, hey, look, I've made the exact same rule. K squared becomes k plus 1 squared. That's what we want. K becomes k plus 1. That's what we want. And so we have proven it. Okay, so here we can write something like, okay, I know that uk plus 1 is equal to 4k plus 1 squared plus k plus 1 if uk is equal to 4k squared plus k. And as part of the k plus 1 statement, of course, we got all this other garbage about that u1 is 5 and un is blah, 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 right? So we got u1 is 5, uk plus 1 is equal to blah, blah, blah. Okay, what else do we got up here? Yeah, okay. And then same thing with this one. u1 equals 5, uk plus 1 equals blah, blah, blah. Okay, all right. And since p subscript 1 is true, and pk plus 1 is true whenever p of k is true, then p of n is true for n is positive integers, right? Okay, and that's it for page 7.